In this video, I'm going to review sampling and sampling distributions. I'll start by talking about populations, samples, and sampling, giving you an overview of sampling and why it's important. So when it comes to sampling, we're talking about the way that we select people or different objects during the course of our study. And these are the things that we use to measure some phenomena that we're interested in. But we rarely ever observe the entire group of people that we are interested in studying. So I've got a couple of examples here. We can think about the health of San Jose State students, or we can think about rates of bicycle ridership in cities in the United States. But we rarely ever study all members of these groups. And so the question is, why is that? Well, that's because it would be impossible for us to do so. Even with something like San Jose State students, that is a huge group of people. I think there are something like 35,000 students at San Jose State. And if we wanted to understand their health, it wouldn't make any sense for us to try to study every individual student. It's the same thing if we want to understand rates of bicycle ridership in cities in the United States. It's going to be impossible for us to actually measure every single cyclist or every single location where people ride their bikes to get an understanding of this, which means that we have to select a sample that we think is going to be representative of the larger group. So we're going to select a smaller subset of the larger group. So our population is all of the cases that we are interested in. And a lot of times in like social science research, we tend to think about it in terms of like individual people. But our population, our cases can also be groups of people, or they can be physical objects as well. So, for example, we might do a study of cities in the United States. In that case, we can think about a city as being a social grouping. So it's not an individual person, it's a social grouping of people that we're using. And so our population is just all of the cases that we as researchers are interested in, and it doesn't just have to be individual human beings. In a lot of cases it is, but that is not required. Our sample is that subset, that smaller portion of the population that we actually wind up studying. These are the people that we actually include in our research. So when we sample, we want to be able to generalize about the population from based on our sample. We want to be able to generalize about the population that our sample was taken from. So when we talk about generalizing, we mean that we want to draw conclusions about the population from that sample. So if we are measuring the health of San Jose State students, and we take a sample of, let's just say 100 San Jose State students, we'd want to use that sample to make broader conclusions about the health of all San Jose State students. And so I'm not getting into whether or not that would be an appropriate sample size or anything like that. Let's just assume that taking a sample of 100 students was appropriate. Then we would be able to draw a conclusion about all San Jose State students. So this is referred to as making predictions or inferences, as another way to word that. But we can learn a lot about a population from a sample. If we carefully select it. So it's not enough to just select 100 students. It wouldn't be enough for me just to select 100 students from my classes and then give them a survey about their health, and we can look at like their stress levels or some other things associated with health, and then try to draw some broad conclusions about all students at San Jose State. That would not be an appropriate approach to sampling. And so there's a question here, and that is, what must be true of a sample in order for us to be able to generalize from it? And this really gets at the heart of sampling. So what has to be true of our sample if we want to be able to generalize about the larger population? Well, it needs to be representative. So we need to have drawn a representative sample. And the way to ensure that a sample is representative is for it to have been drawn randomly, and for every member of your population to have had an equal opportunity to participate. So that is the basic premise, or basic premises, is that we want it to be representative, and in order to do that, then everybody from the population has to have had an equal opportunity of being selected to participate. All right, so I want to move on to cover some language that we use to describe populations and samples. First, there are parameters. These are measures that we use to describe a population. An example could be the average commute time for students at San Jose State, average course load for students at San Jose State, percent of students who take online courses, or maybe the proportion of students who commute by car. So in each case, we are describing all students. We're trying to make generalizations about all students. And so we're talking about our population. And so we would refer to those figures as parameters. When it comes to samples, we use the term statistic to describe our measures. So again, if we're talking about, if we're describing all members of a population and trying to describe something that is true of like every student at San Jose State, we're going to use the term parameter. If we are only talking about measures related to our sample, we're going to call them statistics. Here I've got an example of sampling from your textbook that shows the population. So this is all the members of the group that we are interested in studying. They're on the left. And then we have our sample, the 6 people that we have selected to participate in our research and to represent that population on the right. So you'll note on the left for the parameter, they have looked at the proportion of white respondents. And we see there that there were 15 white respondents out of a total of 25, which is a proportion of 0.6. And on the right, we can look at our statistic and look at the proportion of white respondents, where 4 of our 6 respondents were white, and our proportion there was 0.67. So they are proportions. The proportion of white respondents in each group is fairly similar, 0.6 and 0.67. It's not a perfect match, and that's because we've got a pretty small sample size there. There's a fair amount of discrepancy there. And we're going to talk a little bit more about that difference a little bit later on. But for now, just giving you an illustration of what a population is, what a sample is, and then measures from each one, a parameter and a statistic. Now, just quickly here, I have some review of sample and population notations. These are all things that we've reviewed before, But for mean, we have y bar and mu for the population. For proportions, we have the lowercase p and then pi for the population. Standard deviation is the lowercase s and then sigma for the population. And then with variance, we have the lowercase s squared and sigma squared for the population. Okay, so I want to talk about probability now. And this has been introduced in class before, so this is a bit of review. But this is important. So we're going to start from the beginning here. So a probability is a measure of the likelihood that an event is going to occur. And we represent it with a lowercase p. To calculate probability, we look at the number of times that an event will occur divided by the total number of events. This is actually fairly straightforward when it's presented this way. I think it's a bit confusing, but if you think back to the example with the population and the sample that we just reviewed, we can look at the number of white respondents as being the number of times that our event occurred, and then the total number of respondents being the total number of events. So in terms of the population, I believe it was 15 white respondents with a total of 25 respondents. And then in the sample, it was, I think, 4 white respondents with a total of 6. So it's fairly straightforward. When we express our probabilities, our values range from 0 to 1, where 0 means that the event will not occur, and 1 means the event will certainly occur. And then we can express these as proportions or percentages. So in general, in the text, it presents them as proportions. So we see the decimal. So if there is a 60% likelihood, it would normally be expressed as 0.60 in the text. But we can look at them either way. And if we think about it as a percentage, it still ranges from 0 to 1, but technically we'd say it's 0% to 100%. And so a question for you to think about is, what is the probability of rolling or getting, excuse my typo once again, heads on a fair coin flip? So assuming we're not using a cheat coin or anything like that, what would be the probability of getting heads on a fair coin flip? And that would be 50%. Because if we flip the coin, there are 2 possible outcomes, and we're only going to get one of them. So it's 1 out of 2. So there's a 50% chance. Or we could express that as a proportion of 0.5. And then again, you can see how we might express that. 1 out of 2, 0.5. And if we did 100 coin flips, we'd then expect to get heads 50 times. So what is the probability of rolling a 6 on a 6-sided die? Well, we would say it is 1 out of 6. And we'd represent that proportionally with 0.17. If we were to roll a die 100 times, we'd expect to get a 6 17 times. So then what would be the probability of rolling a 5 or a 6 on a 6-sided die? Well, now in this case, there are 2 possible outcomes, a 5 or a 6. Out of 6 possibilities. And so 2 out of 6 is 0.33. If we were to roll the die 100 times, that means that we would expect to roll 33 5s or 6s. But we can also express probabilities as a ratio, where we write it out first with the number of occurrences, and then we do a colon to separate it, and then the number of total occurrences. So if we're talking about rolling a 6 on a die, we would represent that as, for each roll, there is a 1 in 6 chance. So we just write that 1:6. Likewise, for rolling a 5 or a 6, we would represent that with 2 out of 6, because now there are 2 outcomes out of 6 total possibilities. So I have an example for you on the left there. Like, what is the ratio of people who are widowed? So we can see that there are 127 people who are widowed in our sample there, out of a total of 1,499. So we would express that as 127:1499, 1,499. Here's a bit more information about how we'd actually write that out, and I want you to be familiar with this notation. So we express this as P, and then in parentheses, the condition that we are interested in. So it would be the probability of somebody being widowed in our sample equals 127 out of 1,499. Then we can convert that to a proportion or a percentage just by dividing that. And we'd find that there's a proportion of 0.085, or we could express that as 8.5%. So what's important about this, or how do we interpret it? Well, we can consider the fact that 8.5% is closer to 0 than it is to 1 or 100%. So we would say that there's a pretty low chance that somebody was actually going to be widowed. So an 8.5% chance that somebody is widowed is pretty small. We would also just express that as saying that there is a low probability of that outcome occurring. So when we're looking at probabilities, it's important to note that our observed frequencies are just an estimation of our true probability. And so this is really important when it comes to sampling, is that, again, we are drawing on our sample to make a conclusion about our population. But we don't expect our samples to be perfectly representative of the sample. There's always going to be some variability. Every time we take a sample, there will be a little bit more variability. You can think about this if we did this with San Jose State students. Again, I mentioned before that I think there are about 35,000 San Jose State students. And if we take random samples of 100 students, and we do this over and over again to where, let's just say we take 50 different samples of 100 students, we're going to expect there to be some variability among those samples. And so let's say that we look at the proportion of students who ride bikes to campus each time we take a sample. And so for each sample, we could just ask students, the 100 students, do you ride a bike to campus, yes or no? And they could answer. And so let's say we know that the true probability, if we were to measure every member of our population, if we were to actually ask every single San Jose State student, Let's say it's 13% of students who ride their bikes to campus. Again, that would be our true probability. That would be if we asked every single student at San Jose State, which isn't possible, isn't feasible, and we find out, again, that it's 13%. Well, if we took random samples of 100 students, we would expect some variability, but we would also expect that it would be around 13%. So maybe some would be 12, some might be 14, some might get 15%. We could have some low ones. That is possible that in some samples it might be 7%. Maybe in another sample it's 20%. But we would expect it to hover around 13% if we are selecting random samples where every member of our population, all San Jose State students, had an equal opportunity of being selected to participate. We would expect our probabilities to be similar for our samples. Our sample probabilities would be similar to our population probability. We can get a sense of our true probability if we repeat our studies over and over again. Though if we just keep taking more and more samples, we can get a sense of what our true probability is. And if we did take 50 samples of 100 students, we could then take the average of all those probabilities, and we should probably be at about 13% in that case. If we take that many samples and then take the average or the mean, then we would expect it to be about 13%. All right, so this brings us to probability sampling. And so I've already reviewed some of this, but with probability sampling, our purpose is to select a sample that is as representative as possible of the population. And when we do this, it allows researchers to estimate how different the findings from our sample are from our entire population. Now that's a really important premise here, so I'm gonna repeat that when we use probability sampling, or as I've been describing it, random sampling, it allows us as researchers to estimate how different the findings for our sample are from our entire population. So if we go back to the San Jose State student example I was talking about, where we're looking at like what proportion of students ride their bikes, if we didn't know what proportion of all San Jose State students rode their bikes and we only had information from our samples, we can actually draw conclusions about how different we think the result we got for our sample is from the population, even though we don't know it. And that's the entire premise here of probability sampling, and what we're going to explore a little bit more is that we can actually estimate how much different the result from our sample is from our population. So a simple random sample is our most basic approach to random sampling. And this is these principles here are those that I've already mentioned before. And that where every member of the population has an equal chance of being chosen, and then every combination of n members has an equal chance of being chosen. So those principles are basically the same, but just noting that with n there being the number of members in our group, that any combination would have an equal chance of being selected. So with systematic random sampling, we use a ratio that we can call K just to determine our sample size, and then we'd say that every kth member of our population is selected. I'm not going to go into this too much because we don't use it much, but we can think about it simply where if we needed a sample size of, if we're going to have a sample size of 10, and we have 100 people in our population, then we'd need to select every 10th person in order to have to obtain our sample of 10. And so you start at a random point, and then you can imagine that you would have a list of every member of your population in front of you. So you'd start at a random point on that list, and then you choose every 10th member of the population. There's also stratified random sampling. And we use this approach if we need to divide our population into subgroups for some reason. And so an example of this might be like with San Jose State students, maybe a student's class standing is really important to our analysis. And so we would divide students up into like first year students, and then second year sophomores, third year junior, seniors. And then we would select a random sample from each one of the subgroups. And we would determine the exact number from each subgroup that need to be included in our sample. What this does is it just ensures that you're choosing from each group at exactly the rate or the number that you need to have in your sample. Because like I noted before, if we just draw a random sample, there's going to be a little bit of variability. And we can use race as an example. So let's say that there's just a particular racial group. Let's say we're doing a study of San Jose State students, and race is really central to our analysis. It's about racial experiences at San Jose State. And if there's a particular racial group that we're interested in that just represents a small proportion of our overall population, if we were to just take a random sample, there's a chance that members of that racial group may not be well represented in our sample, because every time we take a sample, it's a smaller subset of our population. And so it could be that racial group isn't well represented in our sample. So we may want to actually oversample that group just to ensure that they are well represented in our sample for the purposes of analysis. And there's nothing wrong with that. We have to acknowledge in our study that that's what we did, but there's nothing wrong with oversampling a particular group just to make sure that they are represented so that we can draw information, or so we can draw conclusions from the information that we collected from them. So that's one way, and that would be an example of disproportionate, where if we're oversampling students from a particular racial group just to ensure that they are well represented for the purposes of our analysis, we would say that the sample proportion doesn't match. Let's say that they represent overall 2% of all San Jose State students, but in our sample, they're 10% of San Jose State students. They're 10% of our sample. So the proportion wouldn't match. Again, it doesn't hurt our analysis or anything like that if we analyze our data appropriately. We just have to understand that's what we've done. Proportionate would be when the proportions in our sample perfectly match that of the population. And so we can look at it, and I forget what the demographics of San Jose State are. If we said it was something like larger San Jose, I think the three main racial groups in San Jose are like Latinx, which is 35%. I believe Asian Americans are somewhere around 30%, and then whites are, I think, something like 27% maybe. And those are the three largest racial groups. I think blacks are like 3% in San Jose. So let's just say that San Jose State is similar. It's not perfect, but if we know that are the demographic characteristics of San Jose State in general, then if it were proportionate, then we would make sure that those proportions were perfectly represented in our sample as well. So our sample should be, 35% Latinx, white, Asian, Black, whatever racial groups we are actually looking at. Okay, so that's proportionate and disproportionate. The idea is here, with stratified random sampling, we're dividing our population into smaller groups, and then we are randomly sampling from each one of those groups. This brings us to the sampling distribution. So again, some review here. We use the term mu, like a cat, to describe our population mean, and we use sigma to represent our population standard deviation. Most of the time, we do not know our population mean and our population standard deviation. Again, this is because in most cases, it's impossible to study every member of a population. Like I said before, even if we wanted to draw conclusions by surveying or measuring the attitudes of every single student at San Jose State, that would be impossible for us to do. We have no way of doing that. We have no way of getting access to everybody who attends. That would be a huge study. It would be impossible. So we draw a sample and use its mean, our statistic, to estimate the population mean. So we want to be able to say that our statistic is representative of the parameter. Okay, so we want to be able to say that the measure we took of our sample is the same or similar to the measure for the entire population. If we take a sample of 100 San Jose State students, and it's a random sample, and that is an appropriate sample size and everything else, given the size of our population. And again, let's say that we find that 13% of all students ride their bike to campus. We want to be able to say that sample mean is representative of the population, and we'd want to be able to say that about 13% of all students at San Jose State ride their bikes to campus. I've put together an example here for you of what this looks like and how this works. So the first thing you'll want to do is to calculate the mean and the standard deviation for all of those cases. So on the left there, the two columns that we have, cases 1 through 20, what you want to do is to find the mean and the standard deviation. And if you don't have, you can do this on a graphing calculator easily enough, but if you want to, you can also just load a website or just do a search for a mean calculator or standard deviation calculator would be the better option. And then you can just plug those numbers in. So this is not an example where I want you to do it by hand. However, if you just want to follow along with me in the video I'm going to show you, I'll show you how to do this in Google Sheets. Yeah, so first you want to calculate the mean and the standard deviation for all 20 cases. Once you've got that, I want you to take two different samples. And so I want you to use those cases. So I randomly selected those. I used a random number generator and told it, I told it between 1 and 20, select 3 numbers at random for me. And those are the numbers that I presented for you there. So it came up with 8, 16, and 18 the first time I told it to do it. So you'd want to take case 8, case 16, and case 18, and then find the mean and standard deviation for those. Then, once you're done with that one, I'd like you to then do that again for case 20, case 6, and case 3. Find the mean and the standard deviation. Okay, so you can calculate those first. And if you want to pause the video and then perform those calculations, I'm going to show you how to do this in Google Docs now. And here's the spreadsheet that I put together and that I shared with you. And you can see here that I just copied over the cases and just as they were presented to you in the slides. But then I did just copy and paste and reorganize them so that they're all in order this way, because it's easier to perform our calculations in Google Sheets to do that. And to do that, I just highlighted it and then I did copy and then I pasted it below. So that's our population. That's all 20 cases. And so our population is just 20 cases. You don't have to worry about what these numbers mean or anything else. I don't even actually remember what they mean anymore. And just know that that is the entire group that we are interested in studying. That is everybody. A total of 20 people, or it could be cities or whatever the units are, but that's everybody. And then I've calculated the mean and the standard deviation down here. The figures are already there for you if you know how to calculate these things, but I'll walk you through how to do this again. So you can see up here in the menu bar that it gives you the code that I typed in to calculate the average, but I'm just going to show you once again how to do this. So anytime that you want to input a formula into Google Sheets, and this is also true of Excel. It might be slightly different with Excel, but they're very, very similar. You type equals. So that tells it that you want to to input a formula in that cell. Anytime you start by typing equals, it does this. Then you can see that for me, it's suggesting what I might want to do. It says based on the data, but I think it's also just based on the things that I've done before. So I could just click on that. And if it shows that to you, go ahead and just do it. But if you wanted to do this manually, you can just skip that. And then you can start by just typing average. And you'll see here that, again, it's giving me that suggestion, but then it also just gives me the option for average right here. So I'm going to click on that because I want an average. And you can see it started and it gave me my left parenthesis. Now, you need to show it which cells that you want it to calculate using. So I'm going to go up, and this is what Google Sheets is expecting now. It wants information about the cells that it's going to perform this calculation for. So I'm going to go up here and click on the first one and highlight it, and you can see that that appears here. It appears here or down here. Then I'm going to hold down the Shift key on my keyboard and then just click on the last cell in the column that I want. And so then you can see that it does C16 colon C35, which is it's just telling you calculate the average for this range. And then I'm just going to finish the parenthesis and put my right parenthesis on there. And then I'm going to click enter. And then that is my mean. Now, if you were doing this on your own and following along, you might have gotten a number with more decimals. And that's because earlier I used this to decrease the decimal places. I forget what it did by default. It may have been 4 decimal places. I backed it up so it was only 1. Then there's the standard deviation. And again, calculating the standard deviation is just as easy as calculating the mean. I'm just going to type in equals. And then this time you'll see it didn't suggest anything for me. So I'm going to start by typing ST. I often forget what these are, but that's why it's nice that it pops up with a list of everything. And then we can see here the first one that's coming up is standard deviation. So I'm going to click on that. And then once again, I'm just going to select all of the cells I wanted to calculate that for and click enter. Now this one is rounded to 2 decimal places. I'm just going to go back to 1 decimal place just to keep them simple. Normally I tell you all to do 2. In this case, it's just an example. It doesn't matter, so I'm not going to worry about it. All right, so that is how you calculate the mean and standard deviation, and then we can see what those values are for our population. That is every member of the group that we're studying. Now that brings us to our samples. And you can see here that I introduced a third sample that I didn't have in the slides just because I didn't have room, but just to kind of help reinforce what it is that we're doing here. And so now I'm going to calculate the mean and standard deviation for those. All right, so I finished all my calculations and put together a couple of new tables, and I'll review all of that with you now. So the first thing you'll notice that I did was that I filled in the values in our tables for each one of our samples. So I just selected, for example, for case 8, I just input this number here. One quick little trick with Google Sheets and with Excel to make this easy is that if I delete that out of there like it was never in there, I can type the equal sign and then just click on the other cell whose value I want to put there and click enter, and it'll copy it over automatically. The nice thing about doing it that way is that if I change what is in here, let's say I made a mistake and that was supposed to be 23,000 instead of 45,000, you can see it changes it there too. So that it can be very convenient when you're doing different math problems, especially if you make a mistake and have to go back and change something. You don't have to change it in a lot of different places. So I went through, input all the values, and then calculated the mean and standard deviation for each one of the samples. Again, if you want to see what that looks like, you can look up here. And so you can see that for this one, I told it to take cells F16 through F18, these right here, and calculate the average. So now I did that for each one of the samples. And you can just quickly scroll across them here, and we can see, wow, they're quite a bit different from our mean. Here, our mean is 59,000, we've got 36,000, 37,000, and then 75,000. Wow, that's a lot of variability. Why is that? Well, the main reason is that these are only samples of size 3. Those are not sufficiently large samples, and so it's going to produce a lot of variability in our results. So that's why sample size matters a lot. So when you have small samples, you get a lot more variability just because there's less opportunity for all the diversity in our sample, in our population to be represented in our sample. So quite a bit of variability here, and quite a bit of variability in our standard deviation for each one as well. So again, and we're thinking here with the standard deviation, how much does each value differ from the mean? On average, how much does each value differ from the mean? And so what calculating the standard deviation did here was it takes the mean of this, which is about 37,000, and then it looks at each one of these values and looks at how different it is from the mean, and then it takes an average of that amount of difference. And that's what the standard deviation is. So with that calculated, again, we can see there's quite a bit of diversity, as would be expected when we have such a small sample size. Now, I went over here in this table, and here I'm looking at the difference for each one of our sample means and standard deviations from our population. So how far away is our sample mean from our population mean? And so this is how different our mean, each sample mean is from the population. I included the population too, just as reference, of course. The difference is 0 because the population mean is the population mean. Sample 1 had a difference of about 23,000. Sample 2 was a difference, once again, 22,000. And then sample 3 was a negative difference, where the mean was actually, we got a negative number here because our mean was actually larger than our sample mean was actually larger than our population mean. So it gave us a negative number. So that's how different they are. And again, we can see quite a bit of variability. I did the same thing with the standard deviation. Once again, we can see quite a bit of variability. However, now maybe you remember me mentioning earlier in the video that we can get closer to our true population value if we take a lot of samples and then we average them out. And so what I've done here with these 3 samples, and what I've represented in this table, is I averaged each one of them. So I took my samples excuse my typo. And I took the average of those. I took the average of my averages or the means of my means. And when we average out our 3 samples, we get an average of about 50,000. That's getting us a lot closer to our population. And then for the standard deviation, we get 32,400, which again, it's quite a bit different, but it's much closer. And then I looked at the difference from the population for these, for when we average these out. And then the question is, how different is it? Well, now we had a difference of about 9,500 for the mean and a difference of 12,000 for the standard deviation. You'll notice that that is smaller than any of the differences over here. So if we take and we average all of our samples together and then compare it to the population, you can see that we get closer. There's still quite a bit of difference because our samples are so small. But if we were to do 10 samples of size 3, we would get closer to the population when we average them all out. So that is the power of taking multiple samples and then averaging out across all of those samples. And that is really important to analysis, statistical analysis, and some things that we'll do in the coming weeks in this class, is that when we average everything out, when we take a lot of samples and average them out, we can be more confident that we have an estimation that is closer to that of our population, if you understand that principle. In a lot of cases, we don't necessarily take multiple samples, but it is important to understand the logic behind this for later statistical analysis that we do. So we won't be getting into that yet. It gets a little bit more complicated, but what you need to understand is that when we take multiple samples and then we take averages across those samples, we get a stronger estimation for our population. Because again, in most cases, we don't have this information. We don't have we don't have all the information for every case. We do in this case because I made the numbers up or I took them from somewhere, and there are only 20, so it's really simple to do. But again, think about all San Jose State students. We don't have any way of having a measure of all San Jose State students. So but we could take multiple samples and then average them out and know that we have a better look or a better understanding of whatever we're measuring among our population. So I'm going to finish up this lecture with a couple of additional points. I just want to talk about sampling error. That's what I was just showing you in that worksheet. So our sampling error is the discrepancy between our estimated population parameter and the real population parameter. So when we took our samples, we were estimating what we think the population parameter is. We were taking our statistic for each one of our samples and estimating our population parameter. Our sampling error is the discrepancy between that estimated value and the real value. And to calculate it, you compare your sample statistic to the population parameter. However, like I've already said many times, we rarely ever know the population parameter. So what this means is that we have this theoretical probability that we call the sampling distribution. So we make a theoretical prediction about all possible sample values for the statistic we are interested in. We look at all possible combinations that could possibly be drawn from our sample. And so going back to my example of San Jose State students, our theoretical sampling distribution would be one that reflects all possible samples of size 100 that could be drawn from all San Jose State students. So again, we have no way of ever doing that. That would be even more difficult than just actually surveying every student, would be to actually try to create all possible samples of size 100 that we ever could. But what we can do here is by theoretically specifying what this distribution is, we can compare our result to it. We get into that a little bit later on. We're not going to go through that now. And to wrap up here, I just want to introduce the formula for calculating the standard error of the mean. And here we are looking at the standard deviation for all of our individual samples. So going back to the San Jose State student example, we could present a distribution, and it likely have that kind of bell shape that we've talked about before, with where we could measure like GPA, average GPA among all San Jose State students. And we could plot it, and then we could calculate the standard deviation for GPA. And we could do that for all San Jose State students. And then we can talk about the standard deviation and how much did students differ from the average. However, what we're doing here is slightly different in that now we're creating a distribution of all potential sample means for samples of size 100. So if we just took every possible combination of students with a sample size of 100 and then took the averages for all of those students and then plotted it out, that is our sampling distribution. And our standard error is the standard deviation of that distribution. We'll talk more about this later. Again, I know it's kind of confusing. How do we calculate that? We take sigma. It's the standard deviation of our population, and we divide it by the square root of our total sample size. All right, I'm going to just end with the central limit theorem. We'll get into this a little bit more later on. So what this states is that if all possible random samples of size n are drawn from a population with a mean represented with mu and a standard deviation represented with sigma, then as n becomes larger, as our sample size gets bigger, the sampling distribution of sample means becomes approximately normal. And that means that it's going to take on that bell shape of a normal distribution. And then we can represent the mean using the mean of our samples, and it will be equal to the population mean, and we'll have a standard deviation that is equal to the value that we get from the formula that I introduced in the previous slide. And so what's the significance here? So once again, we want to think about just collecting a lot of samples. And this is noting that if our sample sizes are larger, then our sampling distribution is going to be more normal, more normally distributed. And that we can calculate what our mean and our standard deviation are for that sampling distribution. And as we've learned about in the previous chapter, then this allows us to compare the results that we get to this theoretical distribution to ask ourselves, how different are our results from all possible results? And so it allows us, this is the foundation of a lot of the statistical analysis that we'll continue to learn about in this class. Well, we will work on this later. I expect this to be unclear right now, but we will dive into this more later on in class.